Hello everyone, how's everybody doing? Okay, so today we'll talk about neural fields representation. It's going to be our last lecture of the semester. So hopefully the end of today's lecture, you'll be able to appreciate what neural radiance view is and the concept of volume rendering. I'll also talk about the limitations of the vanilla Nerf, which is the original Nerf that was published at ECCB 2020. Basically, it has two limitations. One is that it's not able to generalize to new scenes. And then the other thing is that its efficiency. It's very, very slow to train the original version of Nerf. And it's also very, very slow to render it during the inference time. Okay, and then I'll talk about what are the different methods, because it has been 2+ years since the original Nerf was proposed at ECCB in 2020. The paper was actually put on archive in June 2020. And at that time, it was already attracting quite a lot of attention. Okay, and because this was actually the first work that they showed that they are able to use neural networks to encode the whole 3D scene. And this was quite a big thing at that time. Okay, it's still a big thing now, because a lot of people, including myself, we are all actively looking into this area of research. And one thing that I will also talk about is that I'll talk about the difference between volume rendering. So because neural fields or neural radiance fields is just one type of neural field to represent the 3D scene. And in fact, we'll see that I'll explain to you why is it that neural radiance field is not so effective in capturing the 3D surfaces or the 3D information. It's actually very good to do novel view synthesis, but it's actually not that good to do 3D reconstruction. So on the other hand, that was in year 2019, I think 1 year earlier before Nerf was presented, there was a work called DeepSDF, signed distance field. So signed distance field is also a type of neural fields that can represent the 3D scene with higher fidelity. Okay, we'll see why later. But the problem with this is that you need the 3D ground truth. That means that you need the 3D surfaces, the real 3D object, to do the supervision. And therefore, it actually limits it in terms of the training or the real usage. 1 year ago, in the end of 2021, I think, there were several works that I will actually mention, 2 of them in particular, the volume SDF as well as NeRF, where they mentioned how to, or they propose something to convert the side distance function to volume density. Because when you have side distance function, the best that you can do is surface rendering. And surface rendering requires the precise knowledge of where the surfaces are. So therefore, most of the techniques before this, they require some form of mask to tell you where are the objects in the 2D image in order for it to work. And then these 2 works here, volume SDF as well as NeRF, it actually mentions something that without the use of mask, it's able to convert the side distance function directly into volume density, which is a type of radiance field. And then you can directly do a volume rendering instead of a surface rendering from the side distance function to the images. And therefore, this revolutionized the whole game altogether. This means that you now, by using these 2 techniques, either of these 2 techniques, there is no need to do, there's no need to have the 3D ground truth anymore, right? You just have multi-view images, and that would be self-supervised. Then finally, at the end, I'll talk about how we use Nerf and the side distance field to learn animatable and generalizable dynamic humans. Okay, so basically, this would be also a different game, because those works that I will talk about exist from 1 to 4. They are all covering the static scene. So I'll talk about how this animatable and generalizable dynamic humans. That means that if I have human beings in the scene, I want to actually use NeRF or SDF to capture the human. And animatable means that I can then use it as a digital avatar. That means that in metaverse or augmented and virtual reality, I can actually, after I capture the human, I can actually control the human into different poses. Okay, and similarly, I want it to be generalizable. That means that I train the network for a specific human. Okay, for you, for example, then I want it to be able to generalize to me. Okay, and without further training, we'll see how this can be done. And today we have an unprecedented number of papers that I'm going to talk about. Okay, so much that I have to use 2 slides to list all of them. So I'm going to talk about altogether 14 different papers today, covering all the topics that I want to talk about. So just a reminder, I actually showed these slides last week that the 3D surface representations, there are 2 types of it. Okay, the parametric or explicit and the implicit representation. So unfortunately, I realized that because I wanted to also talk about explicit representation. I mean, I'm already like 110 slides. Okay, so too bad. Unfortunately, I won't be able to cover this. But probably if there's time, I might just briefly tell you about it. So I will still focus on the implicit representation today. But today we are going to talk about 2 types of, actually we talked about the explicit representation last week, which was point cloud. But I want to actually talk about this. Unfortunately, I don't have enough space or time to talk about it. So today I'm going to talk about this neural views in particular. It's implicit representation and it's continuous in space. So in particular, I'm going to talk about 2 types of implicit representation, the neural radiance view as well as the sight distance view. Okay, so this just a quick recap of what's the parametric surface. So it's from 2D to mapping to 3D. Okay, so this is obvious because you have any planar surface, you can actually map it into a 3D manifold, which is actually a 2-manifold. Any surface is a 2-manifold because if you stand locally on the surface, you are actually looking at just 2-dimensional space locally. Okay, and this is what we are going to focus on today, which is the implicit or volumetric surface representation. So the definition that is written here, this is actually the sight distance view or a form of distance view where you have at any point, these are all the points that you can sample in the 3D space. Any 3D space, you sample X, which is in the R3 space. And then what happens here is that you would define the surface to be on the level set. So you have a function which takes in the sampled point, and that function will output whatever distance view that is at that point. And sight distance view simply means that you have a surface, and this, let's say this is your X, it will actually tell you what is the closest distance to the surface. Okay, and once you have 0, which is the level set, the 0 level set, then you know that that is actually the surface itself. Okay, sight distance view is one of them, and today we are going to look at 2 of them in particular, the sight distance view and the radiance view. And these 2 are currently the most popular 2 types of representation of implicit representation, which people in the computer vision community and the graphics community, they are both actively looking at right now. Okay, and so the idea of neural radiance view is to do this. Okay, is to do a single view novel synthesis, and this is actually not a new concept. It has been existing for a very, very long time. Okay, so what happens here is that what you want is that you want to give a single input image. And then you really want to, because this image, single view image is looking at the scene from one viewpoint. Okay, so you want to use a deep network or to design a deep network such that you can actually look from other viewpoints. So these are the novel views. Okay, and what you want is to synthesize those novel views. So take note of this, that although we are synthesizing the novel views, okay, in contrast to the generative models, okay, probably you are familiar with GANs, diffusion model right now, things like this, right? I mean, normalizing flows and VAEs and so on. There is a big difference because in novel view synthesis, although you are synthesizing a novel view, this novel view has to be correct to that scene that you are looking at. But generative model, you can generate anything, right? You can generate anything that is fancy or imaginary. That means that you're actually hallucinating something, right? But in novel view synthesis, we are not hallucinating anything. We are trying to figure out what is hidden from that view. Okay? Or you can also think of it as interpolating or extrapolating between views. Right? So that is novel view synthesis. We are by no means trying to do anything or trying to hallucinate anything. So another example is that probably you guys have, I think this is a very old movie, the Matrix, this movie, The Matrix, right? So there is a classic scene in this movie where that guy jumps out and then it's frozen in the midair and the camera actually pans to do a surround view, right? So you know that by doing cameras or by taking camera scene, so let's say this is the guy there, and then you won't be able to smoothly pan the camera from this view to this view, right? Because while he is actually frozen in the midair. So this means that you need all the camera views to take this, all the cameras to take that same view while he is static in the midair at the same time, right? So basically this is not possible because no matter how you do it, you can have a set array of synchronized camera here, but these cameras are discrete. That means that you are sampling at a discrete view, right? So the way to actually pan the camera to render it such that you are able to pan the camera smoothly from one view to another view, that's actually novel view synthesis, okay? Because you are actually trying to interpolate between the view. And this is by no means hallucinating the scene, okay? You are actually interpolating or extrapolating the scene. And that's novel view synthesis. Okay, and this actually is not new. It has been around for as long as 3D computer vision existed. Okay, so it's only recent year that people realize that it can be done using neural networks. Okay, so of course the most significant paper in this area would be NeRF. Okay, and that's the neural radiance field, which was published at ECCV 2020. Okay, so what it suggests is that it proposes to encode the entire 3D scene in the weights of an MLP. So that means that it's actually a very simple architecture. That means that you can actually train an MLP, just this function itself, and it's not even a CNN, it's just an MLP that takes in 5 parameters. Okay, so the input is a 5-dimensional vector, which is the 3D position X and a 2D viewing direction. So let's say you are at this view here. Okay, you would have a viewing direction which is 2D. Let's call it phi and gamma, and then so this viewing direction here is a spherical coordinate that tells you where the ray is pointing to. Okay, and then what you do here is that you sample any point that is on the ray, okay, which we denote as x. And x here is going to be in R3. And then what we do here is that all together we would have 5 dimensions, and you input into a function, MLP, and the output would be a 4-dimensional output, which consists of the first 3 dimensions would be the RGB value, the color, okay, and then the last value would be what we call the volume density. So what's interesting here is that the color, it actually, let's say you are looking from at this point, okay, from this view, and if you look at the same point from the other view, from the other viewpoint here, the color will change slightly. Let's say if I'm looking at this point here, okay, from my viewpoint and from your viewpoint, because the way that light is being reflected into both our respective eyes, okay, is actually different because of the different angles that we're looking at it. Okay, so we will see the radiance, the color radiance to be slightly different. Okay, I'm not going into the detail because the details of this actually, if you're interested, you can actually look at what is called a BRDF. There's a function, rendering function. Okay, that will be computer graphics. Okay, that's why it's an interesting thing that now everybody is looking at, or people are looking at into this. It's both a combination of 3D computer vision and computer graphics. Okay, so then what happens here is that this outputs here would be the color and volume occupancy density. So sigma here simply means that at that point, when you look at this at this point, what is the probability, or what is the rate that light is actually being blocked from this point? Okay, so you can think of it as whether this point, how occupied is this point. If it is fully occupied, then what it means is that light is actually fully blocked. So the volume density will be very high, or will be, you can also actually normalize it to from 0 to 1. So it can be thought of that when you're at the hitting opaque object, then the volume density could be 1. It's actually highest at that point. And so this is all that it actually proposes in this neural radiance field. Okay, and what happens here is that the interesting thing here is that once you do this, you are able to actually render. That means that if I train the function here from multiple views, I have many views here, and then I just simply train this function f theta here, okay, by sampling all the points from different views. Okay, and I want this function here to predict what is the RGB and sigma value of that particular pixel. I can do a self-supervision, okay, because I can actually render this color or back onto the image and do a self-supervision. And I'll talk about the rendering equation later, because this C here, the color, is actually specific to a certain point and a certain direction. But the color that you actually see on the pixel is actually accumulated from every single point. So you have to sample along the ray many of these C and sigma, and then you take a accumulation. You have to integrate over the transmittance, and it will actually form the color at this pixel. So that would be the final rendered value here that you take away with the ground truth. You compare it with the ground truth. Okay, but before I talk about the rendering equation, let's look at because as I mentioned that the color will differ from different perspectives, from different directions, but the volume density will remain the same, because at any point, if it is occupied, from your viewpoint and from my viewpoint, it's still going to be occupied. Okay, so this means that the whole network architecture of this Nerf is just this MLP over here. Okay, and what's interesting here is that you would take in X and then D, And we know that X is the 3D point. Okay, but as I mentioned that sigma, which is the volume density, is independent of the ray direction. Okay, only the color is dependent on the ray direction and the volume density as well. So what happens here is that we'll see that the network, you will directly output your sigma from X alone. Okay, and then RGB, the RGB value would have to, you would have to add a you would have to add a direction to it, okay, because it differs from different viewpoints. And it was also realized in this paper, the neural radiance field paper, that if you simply just input X and D into the network and train it like this, okay, what happens is that the network wouldn't be able to capture high frequency components, because just a 5-dimensional input would be it wouldn't be that expressive at all. Okay, so what they realized is that instead of directly inputting X and D here, it's better to actually put it inside a positioner encoder. So this positioner encoder is just a Fourier basis function. Okay, so what happens here is that all these are the 2, 0, pi, and 2 to 2L minus 1 pi, right? These are the cosine and sines here. These are actually your basis functions from Fourier transform. Okay, and what happens here is that if you do this, because given the input X or P here, in this case here, P, you are able to extend the dimension into very high dimension, okay, by just encoding, because these will be the low frequency components and these will be the high frequency components from P. Okay, so you are able to actually expand it to be a very high dimension, and thus making it more expressive in a sense. Okay, so by just doing this, that means that you take X, each one of the dimension inside X, element inside X, you plug it into this, okay, and then it becomes a vector. So you concatenate these vectors together and then put it into the network. And they realize that by doing this and training the network with this, you are actually able to capture the higher frequency components as well. And thus the whole rendering becomes very sharp. Okay, otherwise it will be blurry if you lose the high frequency component. And so Nerf here, so any target view, by training this deep network, the MLP, you can actually render any target view by doing ray tracing and volume rendering. Okay, so this would be the equation here. If you have a view here, imagine that you already encode everything into F data, where F data is taking in X and D and outputting C and sigma here. Okay, so what happens here is that you have let's say you want to render a new view here. Okay, so you would know the camera position. Okay, you will know where is the camera position, and then you have to specify the ray direction here by specifying D. And what you can do is that you can sample many points from here, okay, and then get all the C and sigma. And the expected color of this particular pixel here, which we are going to call CR, where R here is the parametric representation of this ray. Okay, so this ray would be parameterized by T, which is the camera center O, and plus TD. D is the direction. So you are taking the parameter T. So that means that you are sampling points on that particular ray. Okay, so it will be a function of CR. And this would be the rendering equation, where you integrate from T near to T far. Let's say you want to integrate from here to here. So this would be T near and this would be T far. So we are going to sample all the points from here to here. And then we're going to integrate them together into this in this particular rendering equation, where there are 3 terms inside here. Okay, so the first term here that we'll see is actually the color. Okay, this is directly the output from your Nerf neural network. Okay, because Nerf neural network outputs C and sigma. But note that this C and this final C here is different. Okay, they are different in terms of this C here, the small c here, is just how that color would look like on that 3D point. Okay, by when you are looking at this view. But the final rendering, if you just back project this point, one single point, and then you back project it onto the image, right? You will not get a very high fidelity rendering. Let's say you have a translucent object or whatever, you won't be able to do that kind of rendering. A very good example is that I bet that everyone would have when you look up into the sky, you see clouds, right? Clouds doesn't appear to be flat. There is some kind of layering effect. And that is actually this effect here. Because the layering effect is that because clouds itself, right, is not fully opaque. You can actually see through the layer. It's translucent at some, not fully opaque, but it is translucent to some degree. And what is coming into your eye is actually all the sample of the colors when you are looking at the light ray through the cloud. Okay, so when you accumulate this, you'll be able to see the layering effect. And that's actually what this equation trying to do here. So this term here would be just the color at one point. And then the second term here would be this sigma here. It would be the volume density. And this volume density means that what is the chance, because we are looking at one point, which is RP here. So it's actually the probability of that you are hitting a particle at that particular point, okay? Which can also be thought of as how occupied this particular point is in 3D space. Then there's also the third term here, which is the transmittance. Okay, this is the probability that light travel from T near, because you're starting to integrate from the near point to T, to that point that you are interested in at along that ray, okay, without hitting any particle. That's why it's called the transmittance. This means that if you are going to pass a light from the source across along the light ray, this is actually the probability of how much it can be transmitted across. That light source can be transmitted across. Okay, and this is cumulative. That means that you are actually cumulating the transmittance across, okay, until you hit an object. Okay, and without hitting another object. Okay, so this is the probability. But the problem with this is that if you simply do this, that because what we are doing here is that we are sampling from the 3D space. That means that you cannot do the integration. It is not, although everything is formulated in a continuous manner here, the whole thing is actually, when you implement it on a computer, it's actually not continuous. You would have to sample samples along that ray, okay, before you can do the integration. And this is also the reason why Nerf is so slow, because for every pixel, you need to sample so many samples along that ray in order to just get one pixel. Okay, and imagine that if you have a mega pixel image, there will be millions of pixels inside here. So you need to sample during the rendering. You need to sample so many points, okay, on so many light rays in order to render the whole image. And so the integration is not possible. So one way of resolving this problem here would be to actually numerically estimate this or approximate this continuous integral using uniform samples along the ray. So this means that we can actually convert the integration into a summation. Okay, and I will skip the derivation, but if you are interested, you can look at the supplementary material of that paper. They actually prove how to derive from here to here. Okay, you can actually use the Portugal rule, because when you are integrating, you can approximate under the curve as some kind of rectangles. Okay, and then this would be the final equation that we are going to look at. So the transmittance here would be given by this equation over here, and then there's a second term here, which is 1 minus exponential of this guy. Okay, and Ci here would be the outputs. So basically, Ci and sigma I here, they are the outputs of the MLP, which we talked about just now. And you can actually dump it into this equation. Once you get n number of samples along that ray, you will be able to render it into the color. Okay, so this is why the rendering from Nerf, from radiance field, neural radiance field, it looks realistic. It's not flat at all. Okay, because you are actually accumulating the color samples over the volume density. That means that how transparent that or opaque that particular point is across that light ray. So you are stacking everything together. That's why you get that 3D rendering effect. Okay, and and also delta here is actually the distance between the adjacent sample. So if you have a light ray between sample I and sample J, the distance between these would be delta I. Okay, and so this would be everything about Nerf. Okay, where it's actually very simple. But what is shocking here is that the quality is so good that when they do the rendering, okay, and that actually amazed the whole community of computer vision at that time. And it's actually very simple, but the result is so good that it really just revolutionized the whole community. Because I would say that in the past 10 years or so, it was first AlexNet that took everybody. I mean, it started the revolution on deep learning, and then later on there was this people are obsessed with GAN generative model for quite some time. Then later on, 3D point cloud also took quite a bit of effort from, interest in the community. And now it's the era of 3D, I would say. So a lot of people now are rushing into this. So they suddenly all got interested in 3D computer vision. But it's not easy to start, because you need the background foundation, in order to be able to comprehend. And I would say that even though now the result is good, there are still many concepts in 3D computer vision and computer graphics. It's actually not applied yet, because 3D computer vision and computer graphics is far more than just this. So it's still not really, and I would say that many of the people, you can take Nerf and then you play around with it, right? You can make some tweaks to it, but then in order to make some significant changes to it, you really need the deep knowledge on the 3D computer vision. Right? And yeah, it's so simple, and then that's why it's taking everyone by surprise, and it's quite amazing. Despite the very cool results from neural radiance field, there are limitations to it. So basically, it does not generalize to unseen scenes. Once you are actually optimizing the network over that scene, okay, and you're overfitting to the scene. The reason why it does not generalize to unseen scenes is that because you have a network here, it takes in just 5D input, okay, and that 5D input tells you nothing about that scene. It actually doesn't contain anything from the image. So it's only telling you X, Y, Z and a direction. So there's nothing about the image. So giving it new images won't help. It won't be able to tell you what is in the scene. It's just memorizing. But one problem with this, the significant problem with this is that it doesn't generalize to unseen scenes. So there is at the same time, at almost the same time, there is another work called multiplane images, which is essentially representing the scene with a discretized version of planes. Okay, so this is very closely related to plane sweeping algorithm. Okay, it's actually inspired by plane sweeping algorithm, and this multiplane images is actually generalizable. I'll tell you why. But let's look at how it represents the entire scene with a single input image. So in short, this is called MPI. The representation is so if you have an image, given an image, what it's trying to do here is that it's trying to learn a deep network that produce, so D equals to 1, D equals to 2, all the way until D equals to N, for example. You have N number of planes. So this is your original image. Okay. What it's trying to do is that it's trying to, the network that is designed, it outputs a set of D planes. And these D planes represent a slice of that scene. Okay, so you can think of it that way, that when I'm looking at this scene, okay, the image is here. When I'm looking at the image is looking at this scene here. What happens here is that if you take a step forward and D equals to 1, you slice it here. Okay, that will form another image. And then you take a step forward, you will form another image slice. So what it's trying to do here is that given a single image, it's trying to output all these D planes of image from D equals to 1 to D equals to N. Okay, so once you have this, then what happens is that you can do novel view synthesis from here. And you guys know how to do this, okay, using homography. So when you have a view here, then you can actually look at this by simply projecting all these planes back onto this image. And the reason why you need the depth, okay, the depth planes to form this image and render it back onto the onto a novel view is also because of the same thing, because of the translucent, the transmittance, and the volume density. Okay, so otherwise, if you just take one plane and then you project it back onto the novel view, you will get very flat images. You won't get the kind of depth inside your this, or you won't be that realistic. You see, that the shadings and all this won't be there anymore. Okay, so this is basically the idea behind multiplane images. So this is how it looks like. Given a single view image, is going to produce this multiplane. Okay, and when you have this multiplane, you have a novel view. Okay, you are going to be able to render this back onto the scene. Okay, and the rendering back would be just simply you walk. Okay, this is what we have seen already. It's in your plane sweeping algorithm that we saw how to derive this as well. And the network is actually giving one source image. You are going to have all the colors and everything, basically the image, as well as the alpha density. So this is something like your volume density. Okay, and it actually tells you what is the composition, the alpha composition of that particular depth plane. Okay, and then once you know how to do this warping from the source view to the target view, then you can essentially render image onto the target view. So if you look at this, it's actually very loosely similar to the rendering equation that there are many different versions. The original version is the BRDF version, okay? And that actually is kind of complicated because it takes all into account. So we coming back to your question, if you take into account the surface normal, the reflection, and you stay very close to the original BRDF function, then you will be able to capture everything. But it's going to be computationally expensive, and it's difficult to train to design a network to do that. In fact, Nerf and even our paper we actually all start from that equation and then we simplify it. Okay, right? But there are different ways of simplification. Just now, that version in Nerf we saw, it's also a form of simplification from the BRDF function. Okay, so this is also one of the, this is actually just a weighted sum. You are actually just taking the alpha composition and then you're weighting the sum of this by alpha. We can see alpha here as a weight, okay, and then it renders back to the image. Okay, you can do the same thing for disparity image as well, the depth map, and because you actually have the depth now. Okay, and so what happens here is that in this multiplane images, although it's able to generalize, the reason why it's able to generalize is simply just this here. Okay, because F is your function, is your deep network. It's now taking in the image. So after training, you give it a new scene, a new image, it will still be able to work because you are taking the image directly, okay, as an input. And then, therefore, this particular network here, the MPI network here, it's able to generalize to new scene. But it has a problem here. The problem here, the limitation here is that it directly outputs, it designs a deep network and directly outputs a set of planes of images that sweep across the frontal parallel views of that reference camera position. Okay, and what happens here is that when you render it from other view here, because of the quantization error, then the rendered view, the quality of the rendered view might not be that good because there is a quantization error. Okay, because there is a gap between each individual plane here. Okay, therefore, it's not going to be that good. Okay, and therefore, in this paper here, what we did here is that we simply combine the two, okay, to get the both best of both worlds at that time. Okay, I still remember that this was the second version that we thought of, because when Nerf first came out, they were put into archive in June 2020. So I actually told him about this paper, and then I said that this is going to become the next big thing. We should do something about it. Then, but what I also told him is that it's not generalizable. When I read the paper, I say that this is not generalizable. It cannot generalize to new view. Then the first version that we thought of is actually very simple. The first version that we thought of is that instead of just having a MLP that takes in X and D, then what it gives out the color and sigma. What you can do here is that because you have a view, okay, instead of just this view here, I'm going to put this image through a CNN first. Then I'm going to get a feature map F. From this feature map, I can actually, when it passes through this pixel, I can actually take this pixel here and input the pixel, the feature that corresponds to this pixel into the MLP. It potentially can make it generalizable. So after we discussed this, he went back and tried it out, and it works. It works, and it actually can generalize very well. Then we were about to write the paper, because this was in ICCV. Actually, we wanted to submit to CVPR. Then, as we were beginning to write the paper, we realized that just a few days ago, before we started writing the paper, someone put the paper out into archive, and that paper is actually Pixel Nerf. Okay, so it's actually exactly the same idea. Then we had to throw that away and think of another idea, and then finally we came up with this idea here. That why not? Because I remember that I saw this MPI that was before COVID, 2019. Noah Snavely, the second author of the last author and the second author of the MPI paper. Okay, he actually talks about it during CVPR or ECCV 2019, I think. Then so I remember this paper here. Then I told Jiaxing, and then we discussed about this. Then finally we came up with this version. That the limitation of MPI is that the planes are discrete, right? And the limitation, while the limitation of Nerf is that it's not generalizable. So then why not do this? Right? So the concept here is very simple. Nerf is taking a direction and is sampling points on the ray. So it's actually continuous, right? So why not let's just take MPI instead of sampling a ray. Instead of sampling a ray, we sample a depth. That means that we have this bottom here, and then we still have the direction, right? It's frontal parallel, so we know the direction. But instead of sampling every point on a ray, we sample the whole depth, and then at one depth, at any continuous depth, we output the whole plane, whole image plane. Therefore, our network is actually behaving like Nerf, but it's not a ray sampling Nerf. Okay, it's a plane sampling Nerf. So, but at the same time, we are inspired by MPI because we take the whole source image. That means that we design a network that takes in the source image as well as taking in the depth, a continuous depth. And then this outputs the whole image at that depth. And that's just it. So as a result, we are both generalizable. That means that we mitigate the problem from Nerf, and then we also solve the quantization error from MPI, because now we are continuous. Okay, so that's the whole idea. And I probably won't go through all the details, but I just want to tell you the general idea here. Right, so we call this a planar neural radiance field. Okay, because now we are no longer sampling at the ray. We are sampling at the plane. Okay, and instead of the ray. So this is the idea here. We would have an encoder. It's also very simple. We have an encoder. We have a source image, and then the decoder here will be conditioned on the inverse depth. Notice that we use the inverse depth because if you use the depth itself, then you will not be able to represent a very far away point. Okay, and this would be very bad for the network. So we use an inverse depth, and then what happens here is that now this depth condition on any of the depth will be able to output the whole image plane here, which is exactly the same representation as MPI. Then and the rendering would be the same as MPI as well. So we actually overcome the two problems respectively from Nerf and MPI. Okay? And this is why we call it MINE, because it stands for multi-plane images, or MI, and then Nerf, NE actually stands for Nerf. Okay, and this is a cool word, I think. And yeah, so some details about the architecture, but I'll skip through. I don't think I will go through this. If you are interested, you should read the paper or play around with it. And then we also have the encoding to capture the high frequency components. So these are all the same, where the inputs here, because now we no longer have X and D, okay, the direction. Now the D here represents the depth, okay, but we also do this frequency encoding such that we will make the depth more expressive. Otherwise, it's just one value. If you have just one value, then it's not so expressive. Okay, and we tested this, and you would end up to have a very blurry rendering, or the output images here would have you would have lose the high frequency component. And this is actually a very big discovery, actually. That's another paper on this. it's actually related to spectral biases. Okay, but also unfortunately, I won't have time to talk too much about that. If you're interested, you should look at the paper. Okay, it's actually a very interesting thing here. So to capture the high frequency components, and then the rendering would also be the same as MPI. So once you have the rendering here, we don't do MPI. Okay, so once you have this thing here, because what we output here is not alpha, we output here is sigma. So we are actually closer to Nerf. Okay, that we output the volume density directly here. Okay, so what we do here is that we output the whole 2D image at that plane instead of just one color and one volume density on array, on a point on array. What we do is that we output the whole image and we output every pixel on that image, a corresponding color and a volume density. Okay, then so our rendering equation here directly uses the rendering equation from Nerf instead of MPI, because MPI is just now that rendering equation here. As I said, that they made a lot of assumptions here, and this is an oversimplification because they don't take into account the transmittance and the radiance field here. It's just a weighted sum of the stack of images. So therefore, the rendering here might not be as good as the one that you've seen with Nerf. Okay, so here we adopt the Nerf rendering, and then we are able to get we do the same thing as Nerf as well. So because we are not able to do the integration, so we have to sample near and far. And oh, I forgot to mention that in Nerf, because what happens here is that you have an image and then you want to do a sample. Okay, it would be silly to sample very densely along every ray, because this would be intractable. It will take a very, very long time to train the neural network. Okay, because if you have megapixel image, just to render that image, and if you sample so densely along the ray, then you will need to it will be an astronomical amount of samples that you need to sample, okay, in the entire scene to form this image. So what they do here is that they actually split the training into two stages, from coarse to fine. Okay, because the obvious choice of where to sample is that you need to sample near the surface. Okay, let's say I see this monitor here. I have a ray that passes through here. It doesn't make sense to sample the empty space. You should be sampling around along the light ray that intersects here. You should be sampling close to the surface. But the problem is that when you first initialize the network, it won't give you anything. You don't know where are the surfaces. You only know where is the image. Okay, so you don't know where to sample first. So this is the reason why they split it into two stages of training. The first stage is that you sample coarsely. So you do a very coarse sampling to save the computation. But when you do a coarse sampling, you won't have such a good render of the image, right? But then what it will help you is that it will help you to initialize your network such that it knows roughly where the surfaces are, right? Then in the second stage, you do a fine sampling because you know coarsely where are the surfaces. Then the fine sampling in the second stage, you will sample near those surfaces, densely near those surfaces. And that actually helps to speed up the training and also improve the quality of the final result of Nerf. Okay, we do the same here as well. And then so all these are the math. I will skip this because you already know all this. Okay, so when you have a new view, you just warp it and then you render it back using the rendering equation here. Okay, and here's some of the losses that we use where you have a rendered view and the ground truth view. So we use a video. That means that the video data set, you have a video that takes around the scene. It's a static scene that we see. And then what happens here is that you just need to take any source view from one frame, okay, and then you try to render it onto a target view or many target views in the scene to train your network using this loss function. So there are several loss functions. There's this reconstruction loss, which is the L1 loss between the photo consistency two views, okay, and then the SSIM, which is the structural similarity loss, and we also have a depth smoothness loss. I actually mentioned all this before when we talk about the stereo using deep network, left-right consistency stereo. Okay, so what this means is that I want to actually make sure that the color gradient and the depth gradient are smooth. Okay, so therefore I want to minimize this gradient here, and also we first perform structure for motion, okay, of the scene, and then we supervise the depth based on the sparse depth that we get from structure for motion. Okay, and then and also we also take the scale from the structure for motion to fix it at a certain unit scale. Okay, and then we try to normalize away the depth with the scale calibration. So this would be the scale calibrated loss. And here's some results that we get. Okay, you can see that compared to MPI, because MPI has that quantization error, as I mentioned, that along the planes there are gaps in between. Okay, but ours is continuous. So that means that you can sample densely along the ray and you render it into the target view. Therefore, we are able to actually render better quality of the image compared to the ground truth, and you compare it with MPI. Ours is actually better. Okay, so here's some results of the novel view synthesis. Okay, and in fact, the street view dataset, this kitty dataset, is actually very difficult to train. Okay, because the reason why it's difficult to train is that because the car is always traversing in a straight line, and when you do the straight line traversing, right, you don't see too much parallax of the scene, and therefore this rendering here actually, because you are always moving forward, so this rendering here can be highly subjected to degeneracy. Okay, but yet we still manage to get it pretty much nicely. Okay, so here's mine, which actually makes it generalizable as well as mitigating MPI. Okay, and I think this is a very nice work, a very neat work, which is called the IBRNet. It's actually generalizable. So it learns from, so unlike the it also has the same concept, you know, like the same concept of, in order to make Nerf generalizable, you need to make the inputs as the image or the image feature. You can see that what they are doing here is that instead of so you have a target view here. Okay, they have multiple source views that are close by. And what happens is that they take the image feature. So they put each one of this image into a deep network, 2D deep network, to process the image into a feature map. Okay, and then you have this. If you are looking at the render of this pixel here, so you will sample many points along the ray as well. So let's say you are sampling this point. So what it does is that, because Nerf, it also needs known poses. Okay, so this is also one of the limitations of Nerf. It needs known poses. So far, whatever that I've talked about, it needs a known pose. Okay, I'll talk about BAF later, which does bundle adjustment together with Nerf. Okay, together with Nerf. But BAF is also not perfect. Okay, I will tell you why later on. What this IBRNet does is that you process and then you collect all the features from multiple views and you aggregate it here. Okay, and then you aggregate it here and you collect multiple samples along this ray in the same way after you aggregate from multiple views. Then you dump it into a ray transformer. Okay, so essentially, you dump it into a ray transformer to aggregate based on the self-attention and cross-attention. You put it into a ray transformer here. So in the paper that we have to make the structure for bundle adjustment generalizable, we actually leverage IBRNet. Okay, and I also have a third paper in this year's CVPR on Nerf. Okay, and that is actually from synthetic to real transfer. Okay, we also leverage this now. So instead of ray transformer, what we did was that we actually do contrastive learning on the ray over multiple views. That's why we call it contra Nerf. Okay, so anyways, okay, coming back to this. So we can aggregate this and then put it into a ray transformer, such that this ray transformer here will output the sigma over the different location of the ray. Okay, and this sigma here, it's the reason why they put it through a ray transformer is that because the opacity or the volume density across the same ray, right, it should be influencing each other in a way that, because when you have an object at that point, so you need to know where the free space are and where are the other objects on that ray. So in order to produce the smooth volume density across the whole ray, that's why it needs to be placed into this ray transformer, because this has got to do with occupancy. Okay? Whereas the color would be just based on the direction and that point in space. Okay, so the color will be predicted first. You don't have to put it through the ray transformer. Okay, and so I have already told you about this overall view. But what's interesting here is that, okay, so this is the architecture, okay, of it's very simple. And what's interesting here is that this is the reason why it's generalizable, as I mentioned, is that it's actually taking in the feature from the image. There's no more just purely based on the direction and the 3D point. Okay, and it's also IBRNet. It's also leveraging the multiple views. Okay, that you can see that at the end here is actually aggregating the colors from the multiple views. But let's look at the detail of every step. So first, as I mentioned, that given a source view or a target view, okay, you look at the point on the ray, and then you check all the corresponding. So given this source view here, you look at a point, you check all the nearby views, the nearby source view, and then I'm going to collect all the image features here, which I'm going to call it F1 to Fn, n views altogether, n source views altogether. And mu here would be the mean of all these features. Okay, and V here would be the variance or the standard deviation of actually it's the variance of the feature. So you can easily compute from a d-dimensional feature map, okay, a feature vector here. So what they do here is that they concatenate this together. So this actually gives the local information of that pixel, as well as the global information from multiple views. Okay, because F is local to each image view, but mu and V, they are aggregated across all the multiple views. So by concatenating them together, you would have both the global and local information, okay, and therefore it's multi-view aware. Okay, and then this, you input it into an MLP, it will give you this is something like a point net. Okay? It's something like a point net where MLP, where you leave the dimension of F into the input vector here into a higher dimension, okay, which is into another dimension, actually. Not another dimension, it's the same dimension, but you map it into another feature here, f prime. Okay, and then we will also output it, we will also output a set of weights, corresponding weights here. Okay, where we'll concatenate the new feature with the weight, and we'll do weighted pooling. Okay, that means that instead of max pooling or min pooling, we do a weighted pooling. That means that you take a weighted sum and pool them together. Okay, before you input into another MLP, which gives you F sigma, that's the density feature. Okay, which we will then use it to predict the volume density. Okay, so now you have this density feature from one single point, okay, on the ray. We'll do it for multiple points on the ray, the same way to predict. So we'll have many F sigma here. Okay, then we'll put it into the ray transformer here to get the density. Okay, we'll get the density for other sample as well on the same ray, because it's a ray transformer. Transformer, whatever that you input, you output the same dimension. Okay, and that's the idea behind a transformer. So the positional encoding and the multi-head and self-attention here in the ray transformer will tell you the relation along that ray, all the features along the ray. And finally, and then the color prediction here would be, because you have the weights here. Okay, so what we will do here is that we'll concatenate the feature F here with the delta DI. Delta DI is simply the viewing direction. So you have a source view, a target view. So this direction here is D. Then from another view, you are looking at that point. Okay? From another view, this direction here, which will be DI. So I'm going to take the delta between these two views, okay, and then concatenate it to and concatenate it with this feature over here. Before I put it into MLP, and this MLP here will output a new set of weights. This new set of weights would be what I use to aggregate the color. So I will not predict the color. I will not design a network to predict the color. Instead, what it's trying to do here is that for every view here, I'm going to collect those source views here that corresponds to this point in 3D. I'm going to collect all the color, C1, C2. This is my target view. Okay. And then what I'm going to do is that I'm going to predict the weights for each one of the pixels that corresponds to this. And I'm going to take the weighted sum. This pixel here, this point here would be taking the weighted sum of all the colors, okay, that I'm going to collect from the multiple views. Okay. But this weighted sum here, this color, is not the color that I'm going to render here, you know. Okay. It's just the point, because it's the direction, it's just that point, the color on the point. Okay. Because in order to render this pixel here, I still need to do this. Okay. And I still need to do this, where this C here is the weighted sum C here that I'm looking at. But I need, in order to compute this, which is this guy here, I need to sample many points here, which is the aggregation, and then I integrate it and together with the volume density and the transmittance. Then I'll get the final color here. Okay, so this is how IBRNet does it. It's leveraging on the multi-view. Okay, but IBRNet also has a disadvantage. It is that it does not work on one view. Because if you only have one view, right, then you won't be able to compute all this mu and v. Okay, it will not be robust. So it needs to have many nearby views in order to make it robust. So I think that we tested this. You need at least 3 views, I think. 3 nearby views in order to make it work nicely. Okay, so the loss would be just this, as it's the same training as Nerf. You have a coarse stage, and then you have a fine training stage. Okay, and you gradually do this. You can see that the IBRNet is actually rendering everything very nicely, even compared to the original Nerf. Right, so it's actually, and the cool thing is that it's actually generalizable. And the reason why, one of the biggest reason why it's robust to the, it's able to produce higher quality rendering is because it's not predicting the color, it's aggregating the color. Okay, so it won't deviate too much away from the nearby views, and therefore it's actually kind of robust here. Right. So we saw that the first disadvantage of Nerf was that it's actually not generalizable. So we saw that from using MPI, you can generalize it. Using MI, you can also generalize it. And IBRnet, you can also generalize it. Okay. The other disadvantage of Nerf is that it's very time consuming to train and render. Train and test. Okay, both are very time consuming. Because during training, you have to sample so many points. Then you have to render. The rendering is also very expensive to render the whole image. And usually during training, the original Nerf, they don't sample the whole image. They don't render the whole image. Per image, they only sample 1,000 points. Okay, and that will actually mitigate the computational complexity. But then it's still very expensive. It takes at least like 3 days to train Nerf. Okay, then it came in 2021. There are right now many papers on to speed up Nerf. Okay, so this Octrees is one of them. This is for rendering, but the training is equally slow. I'll tell you why. Then the follow-up of this, which is the Panoxer, it's both the training and the testing is fast because there's no deep network in that at all. I will tell you after this. Okay, so naive Nerf is very slow because it requires dense sampling where every point needs to be sampled. Okay, and the reason why rendering is slow is because the query depends on the viewing direction as well as the spatial position. Okay, you need to sample every point. And what happens here is that because, as I mentioned, that the color, okay, the color is dependent on the viewing direction. Therefore, you cannot cache the color. You cannot store it somewhere. You cannot just take one view and then try to compute the color. So the color here, C1, C2, and so on. Okay, you cannot just put it through you cannot just take the direction and the point X and then use the deep network of Nerf to output the whole set of color and store it somewhere, and then reuse this color when you are trying to render another view. This is not possible in Nerf because the color is view dependent. It depends on the direction. So that means that every image that you render that is a new direction of the view, you have to resample everything again and do the rendering equation. Okay, so but it would be different for the volume density. Volume density is direction independent. That means that you can actually take this, just one view, and then for every point on the ray, you sample the volume density. You can store it somewhere because you know the spatial location X. You store it somewhere you cache it in somewhere. Then given another view, because it's view independent, given another view, you can still use back that same volume density. But this is different from color. Color, you can't do this. So the idea here is that if you can find a way to decouple the direction with the color from the color, right? Or decouple the color from the direction. That means that you make color independent of the viewing direction. Then you can cache it and make rendering fast. That means that you just need to do it once, right? You store it somewhere, then you can actually render it from any other view. okay, by reusing all the color and the volume density. So this is exactly what an Oct3 does. So what they realize is this. They realize that just now I talked about the Fourier series, the Fourier encoding. So Fourier transform actually. This Fourier series, just now the Fourier encoding is actually a form of basis, a linear combination of the Fourier basis. But there is something called the spherical harmonics in 3D. Okay, this is equivalent to Fourier series in 2D or in using I mean when you do signal processing, right? But in 3D, when you render the color, okay, of the sphere, okay, there's something called the spherical harmonics. So basically, you can decompose the color into a linear combination of coefficients k. So you can actually take a linear combination of the coefficient k and the spherical harmonics basis. Okay, where the interesting thing is that now the spherical harmonic is the one that is dependent on the view direction, but it can be computed in closed form. So there is no need to learn because it's a basis, it's a set of bases that you can predefine and compute it in closed form. Okay, so what happens here is that if you are viewing it in this direction, and then all you need to do is that you sample any point here, right? So you would have a direction, and a 3D point and an X here. But what they do is that they redesign this network to output K, which is the coefficients of your spherical harmonics. And K is actually independent of the viewing direction because they shifted the viewing direction to the spherical harmonics basis, which can be computed in closed form. So now there's no need to learn whatever that is output from your network, right, is totally independent of the viewing direction. And the part that is dependent on the viewing direction can be taken out and computed in closed form. Okay, so what happens here is that if you train it based on this view, you have K here, the coefficient, and then now you decide to look at it from another view. Okay, this point here, that K that you compute from this view still remains. Because the spherical harmonics here, you will take in the viewing direction. Okay, so that means that you use the same K, but when it's going to be a linear combination, okay, you have K and then I and spherical harmonic I, depending on what's the order of the basis that you use. So it becomes a linear combination. The color will become this. Okay, but this now, the K here is view independent, which means that you can cache it together with your volume density. Just given one view, you cache everything in the 3D space. And then when you change a different viewpoint, all you need to do is that you recompute the spherical harmonic. There's no need to put it through any network anymore. Okay, so it becomes very fast during rendering because you decoupled the viewing direction now. Okay, and what is even interesting is that they make it even faster by saying that given one viewpoint here, right, or one image here, if you want to do novel view, you just use this and then you put it through a network. You put it through a network and you give all the density and K, okay, of every single point in the, so you can think of it that this way, that I will do this and then I will sample densely on this, all the points, and compute all the density and K which are view dependent, or view independent, sorry. And then I'll cache it somewhere, but I don't cache everything because not all the points here in the 3D volume is occupied. So what they did is that they store it as a Oct3. That means that they store directly only those points, the K and the volume density, where it corresponds to a surface. where the object is. Okay, and when you have a new view, when you decide to do you decide to query a novel view, then you can actually search through the Oct tree very efficiently. So not only that this thing here can be cached, it can be also cached and retrieved very efficiently. Okay, and this is how they manage to. This is the function here. Right? So k is coefficient. This is the spherical harmonics which can be computed in closed form, and so now they can actually render this in a very nice way. Okay, but then the problem with this Panel tree is that although the rendering is fast, the training is still the same. The training is still the same because there's no change in the output dimension. Okay, k is still in 3 dimension. You still have the RGB coefficient, and you still have that means that you still have the 4D output and the 5D input. So the network here, there's no change to it. It's just that the very subtle change is that now it becomes view independent. So that actually helps to reduce a little bit of the training complexity, because now your network doesn't have to learn something that complex anymore. Okay, and the document in the paper that claim that there's about 10% faster. Okay, so the Panel tree is about 10% faster. Okay, but the training is not as fast. Okay, so in the follow-up paper by the same guy, okay, which is CVPR 2022, because Panel tree still requires training time. So what they do here is that they say that in Panopser, they say that forget about deep networks. We don't have any deep network at all. So there is no more training time at all. Okay, but instead they do optimization. So what happens here is that so instead of a Panel tree, because now there's no need to cache the coefficients and the volume density anymore. Okay, but what they do here is that they discretize the world into a regular tesselation of boxes. Okay, and at every edge here, they attach a spherical harmonics. Okay, and this spherical harmonics is still dependent on the viewpoint. Okay, so this spherical harmonics here is dependent on that viewpoint. And then given a training image, okay, although it's saying that training image, but actually there's no training. It's just an optimization. You don't train any network at all. So what happens here is that you still have that linear combination, okay, from this view here, but because you have a quantization error, which is you have the spherical harmonics for these 4 points. Okay, so what happens here is that let's say this point here, it intersects at this point here. Okay, this would be a linear interpolation of all the spherical harmonics from the 4 corners, from the 8 corners of the boxer. Okay, and they optimize over that volume density here, as well as the final spherical harmonics that you can get here from all these 8, from the linear interpolation of all these 8 nearby spherical harmonics in that view. Okay, so once you optimize this, you minimize this over the reconstruction error and the total variation error. I talk about this. The total variation error is just that you make sure that the nearby boxes have the deviation away. Okay, the deviation of the color shouldn't be too much. Okay, so what they do here is that once you have done this, okay, you would have gotten the coefficients for this particular point over here. So you can sample from this view, you can sample everything. And then if you have a new view, you just need to project everything back or render everything according to the coefficients that you have computed from the optimization here. And also the spherical harmonics will change will be recomputed based on the new direction. Okay, and this means that since there's no more training, okay, then everything will become super fast. And it only takes 11 minutes to do this optimization because it's just interpolation. It's sparsely across the scene. And therefore, it actually, this paper was also kind of impressive when it first came out. It's 11 minutes of optimization time, and it renders at 15 frames per second. It's so fast. It's actually, so those who are doing robotics, right? We always say something is running at real time when it's more than or equal to 13 frames per second. So this is 15 frames per second. It's amazing. It's really amazing. And it takes 11 minutes to optimize. Okay, so here's the total variation and the reconstruction error. The reconstruction error basically is the same thing. Okay, and yeah, so here's some results of Panoxer. Even though there's no training at all, you can see that it actually gives better result than Nerf. Okay, the reason is very simple. The reason is because of the spherical harmonics is able to capture the variation of the color very well. Okay, and that's why it gives actually very good results. Right. So despite Planol 3 and this Panoxers being so fast, right? There is still a downside of it, right? So because Panoxer there's no training, you basically what it's trying to do here is that basically it's optimizing. It's kind of impressive, but what happens here is that you still need to do some form of frequency encoding, all these kind of things, right? So in just very recently, which is SIGGRAPH last year, 2022, there was this paper called Instant NGP. Okay, it managed to speed up the training because comparing with Panoxer, which there's no training, it's just optimization. So what happens here is that for every scene, you need to optimize, you need to do this kind of optimization, and the result that it gets will not be as good as if you use data to, MLP or any neural network to learn something, and then you try to render it into a novel view. So it kind of defeats the purpose of having a data-driven approach or deep network, right? There is still something lacking there where you are not utilizing the strength of deep network. So Instant NGP, not only that it's able to speed up tremendously, it also, what it's doing is that it's able to speed up both the training and the testing tremendously, right? So you still train a network, but now instead of a few days, it reduced to a few minutes to train the whole thing, or a few seconds, I think. The whole network can be. And what's interesting here is that in the original Nerf, okay, when they do the Nerf, they realize that if you don't encode, no encoding, okay, that means that you don't do the frequency encoding as I've mentioned earlier on, right? The Fourier series. If you don't do that, then you only have an MLP. Okay? The MLP would be 4,000, and let's say you have 411K. They train this network for 11,000 steps, and they compare the two with frequency encoding and without frequency encoding. This was the original Nerf, and this was just simply remove the frequency encoding. Then you can see that the quality of the result is very different because all the high frequency components will be lost. Okay, because the reason is because now you only purely have a 5-dimensional input. It is not so expressive anymore. But if you encode it, you're actually equivalent to lifting the 5 dimension to a higher dimension using the frequency encoding. Right? You are actually using the Fourier basis to encode it into a higher dimension. So it helps to make it more expressive. And thus, you get more details capturing the higher frequency components. And therefore, in this paper, they observed this thing here. So they thought that why not? Because encoding makes the input more expressive. But encoding, frequency encoding itself, there is no learning. So why not? Let's shift the learning part to the encoding. Okay, so what it means is that you can have an MLP. This MLP remains. This is the original Nerf MLP. But the original Nerf MLP is that it takes X. Let's call the input as X. Then it does an encoding here. Okay, before it puts into this MLP and outputs the color and sigma. So by doing a fixed encoding here, it's already able to make the whole thing improve the result by so much. So in instance MLP here, they say that why not let's also do a MLP here and learn the encoding, right? And so merely this talk itself, they did some experiments here, and the result was amazing. So you can see that here there's zero parameters, but this is with the frequency encoding. MLP is this amount of parameters to be learned. So what they say is that, let's say if I do this, because up to this point here, they are all spatial. Because what you have here is that you have all the points spatially in the 3D point along that ray. Okay. So what they are, so this part here, if I were to take a volume in the 3D space that I'm interested in, and then they say that, oh, let's sample very densely on every single ray on this volume, right? Then we put all these points and encode it into an MLP here. So there's another MLP here. We sample very densely and then put it inside here, right? Then we can reduce the number of parameters. So the first parameter here becomes 10K, which means that the original Nerf network becomes 10K parameter. And this MLP, let's let it be 33.6 million. Okay. And what they show here is that the result is amazing. Okay. You get almost the same quality as the this counterpart here, the frequency encoding here. But now you are actually shifting the burden towards the spatial encoding rather than the actual MLP. Okay. And I'll tell you later why is this so amazing. Why is this so important? Okay. So now they also try it on dense grid at multi-resolution. That means that you form an image pyramid and then you sample along the ray, right? And you can see that again, the MLP, the original Nerf MLP drops to 10K, but you have 16.3 million in this spatial encoding here. You will get almost the same performance, and the training time now drops significantly. So this value here is the training time. It drops significantly, and the reason why it drops so significantly is this. Okay, because in the MLP here, if you have all your parameters in the original Nerf MLP, so whatever input that you have, because these are all in feature space, in the feature space of your deep network. So when you do a back propagation, right, you have to back prop to every single parameters inside the Nerf MLP. But imagine that you have a dense, because this encoding here is spatially arranged. It's spatially arranged. So when you have an array that passes through, you only need to update the weights along that array, okay, of this MLP here, because it's spatially arranged. So that's why the training time drops, because when you do back prop when you shift the number of parameters from here drop to 10K, and you shift it to the MLP of the spatial encoding. During every backpropagation, you don't have to update all the 33.6 million parameters. You just need to update those that are spatially along that ray. Okay, I'll show you an illustration later that is shown in the paper. So therefore, the training time becomes significantly faster, and as well as the inference time. Because when you do inference, forward propagation, you also only affect those that are on the ray spatially. Okay, so every time you do this, it's going to be, whereas if there are a lot of parameters here, then it will affect all the parameters when you do forward propagation. Okay, so what they, and instead of even doing a dense grid, they make it even faster, because when you want to retrieve those parameters that are along this ray, okay, if it is just a regular grid, then basically you have to search through everything. The retrieval is not so efficient. So what they say is that they propose a hash table. It becomes a query and key. Okay, you have actually, you do a hashing. That means that along this ray, you just need to retrieve the parameters, spatial parameters that are along that ray, okay, using the hash table. And when you update, you also use the hash table to update those parameters. And therefore, the training time, you can actually have a significant number of parameters here, but then the training time drops. Okay, and what happens here is that they even make it into a hierarchical way. Okay, so the multi-grid, there's a multi-resolution of the grid. Okay, so you can imagine that, let's say this is the, we are looking at 2D now, okay, for illustration. This is actually shown in the paper. So imagine that if I have X and X passes through this point here. Okay, so what I want to do is that I want to retrieve the feature of this point. Because I'm storing all the features as a grid, multi-resolution grid. So I would have, now it's showing level of 2. Okay, there are 2 levels here, more fine level as well as a coarse level. Okay, and if you have a point here, X is here, then what you want to do is that you want to actually retrieve at every level 2036, which is actually the 4 points where that encloses that X that you want to retrieve. Okay, then from here you interpolate, you get a feature here, and at the other level you also retrieve 0417 using a hash table. Then you interpolate, and then you get the other part of the feature, okay, that you retrieve from the interpolation of this, and you concatenate them together. There's also a bias term here. Okay, so there's also a bias weight here that you learn. And then from here, you can notice that now your features, this whole part here is the encoding part. Okay, so what happens here is that the parameters that you need to update when you want to update this point here, okay, it's only these few parameters that is close by to that query point. Whereas all the other points, all the other features of this network, the encoding network data here, okay, it won't affect this point. So it becomes very efficient. The retrieval becomes very efficient. The update also becomes very efficient because you have a hash table. Okay, and it only affects locally that point. Okay, because everything now is arranged in a spatial manner. And whereas, because you are shifting the burden to this encoder, okay, because it will make the Y here more expressive now. Okay, you are learning it to be more expressive, but at the same time, it's so efficient to update it. Okay, and what you can do is that you can reduce the size of this. This is the original Nerf MLP. You can actually reduce the size of it because you can see that this is fully connected. If you have a feature here, which imagine that now, let's say I encode using frequency encoding, the original Nerf, Then I have to have a big MLP here. And this big MLP here, there's no way to decouple them. One forward pass and one backward pass will affect everything. All the neurons inside there, right? So in this way, it becomes very, very effective and very fast. And this paper is so cool. It actually speed it up by so many times that now I think a few seconds, the Nerf is done training. Okay. And it's really amazing. So this is how they all the parameters that they have, and the memory the complexity, and you can see that they have gigapixel image, okay, where if you train for 1 second, this is what you get, and then if you train for 60 seconds, okay, you can actually zoom it into a very fine resolution. So megapixel or gigapixel means that you have to do all the sampling, all the rays so many times. Okay, and this is just too amazing. Okay, whereas Nerf will not be able to do this. But there is a disadvantage of this. Anyone can tell me what is the disadvantage before we go for a break? Or no one sees the disadvantage? Yes, it's not generalizable. That's the disadvantage. But why? Why is it so difficult to generalize this? Any thoughts on why is it so difficult to generalize this? Yes. Yes, you are correct. So the reason is because of this. Just now I mentioned that Nerf is not generalizable because it takes in X and the direction. Okay, but now, so the way to generalize Nerf is that you make it dependent on the input image instead. Okay, but now you're actually entangling the whole thing here, spatially to X and the direction. So all the parameters that is learned, because you are actually, this is the encoding, is actually dependent on the viewing direction and the 3D point. So it no longer becomes so easy to disentangle this. Okay, and that's the reason why it is not generalizable and not so easy to generalize it. Okay, any question? If not, let's go for a 5 minutes break. Then I will talk about the remaining parts. We come back at 2035. So there's another category of this the neural fields, and that's actually the side distance function or side distance field. And what this side distance field is that given any point on the 3D space, let's say you have this, this actually has a name. It's called the Stanford-Barney. What happens here is that, let's say I look at one slice, just the two-dimensional area over here. And what you get is that, let's say I query any points on this, any point, and I call it X. Okay, the side distance field will tell me the closest distance from this point to the surface, to this surface boundary. Let's say if I have a surface boundary, the side distance field will tell me the closest distance. Okay, and it will be more than 0 positive when it's outside the surface. And when it's inside the surface, it will be less than 0, it will be negative. So you can actually figure out whether you are inside or outside the surface. But there will be a problem if your surface is an open surface. Okay, so and then when you're exactly on the surface, it would be the level set of 0. Okay, it can be also there are also other representation like the occupancy representation, where it ranges from 0 to 1. The level set will be either at 1 or 0.5. Okay, so that's also, but in terms of the occupancy probability, there won't be a distance. You won't know exactly what is the distance of that point to the nearest surface. Okay, but side distance field has this. And in some other representation, you might also have unsigned distance. That means that you don't care about whether you are inside or outside the surface. You just care about the distance away. And there is also a truncated sign distance. That means that you only care about up to a certain point. Okay? Because the distance will go infinitely large if you go very far away from the surface. So you truncate it at a maximum value, and all the rest of the value will remain the same. That would be the truncated sign distance function. And so in 2019, this paper, DeepSDF, was the one that pioneered the learning of the sign distance function using deep network. Because essentially, sign distance function is just a function that takes in x, which is a 3D point in the volume, and then outputs the sign distance value, okay, the SDF value. And what you can do is that you can parameterize this f with a deep network, and then you can train the deep network to directly regress the sign distance function. It's a continuous sign distance function given any query points. Okay, but there are challenges if you do it blindly like this, because deep network essentially is very bad in doing regression. Okay, and you do x, and then it outputs a SDF unbounded. This is really going to be challenging to let the deep network learn this. Okay, but if you can do this, directly regress this, then the zero level set would be actually your surface, okay, the object surface. But the challenge is, as what I have mentioned, it's difficult to learn this. So in this deep SDF paper, they mentioned a few variants of the network. So the most direct one, which is the most naive one, is that directly I learn encoder here where or a network here, just a network here where I give XYZ a point in 3D, and then I use it to regress the SDF, okay, where the level set when it's equals to 0 is actually the surface. So you need to parameterize the network using data, and then you need to train this to make sure that it outputs the regress value. Okay, and training is usually done by, you need to have the real SDF values. That means that I need to use the 3D surface, the 3D object as a supervision. So this is also the disadvantage of SDF, because you need the 3D object to the 3D ground truth in order to do the supervision, because there's no way to render this back. Okay, what you have here is just on the surface. It's just the surface, the level set of the surface. There's no volume density or transmittance per se, because the transmittance is actually a function of the volume density. So once you don't have the volume density, it's not possible to do volume rendering. You can only do surface rendering here, but surface rendering won't give you the realistic image. Okay, what is commonly used is that you can do sphere tracing or ray tracing. That means that you trace across the ray and then you check whether it actually hits the surface or not, or the level set, and then you render it back. But then it will be a flat image. You won't be able to get because there's no volume density. Okay, so training is usually done by clamping it. So this is a form of truncated sign distance actually, where any value more than delta, you don't care about it anymore. Okay, otherwise it will become unbounded. When it becomes unbounded, basically it's not possible for the network to learn well. So here, if you do it naively like this, the shape information is actually contained inside the network. So that means that you are overfitting the network to just one shape only. Okay, and there's no chance of doing any refinement anymore. Okay, so basically you overfit to that shape. You cannot actually use it for other shapes. Okay, after you train the network. Therefore, they also propose a second variant where instead of just inputting XYZ, they have a code here, okay, a latent code here, where this latent code can help to capture the shape information. So it transfer this the network the encoding of the shape information in the network to the code. And what happens here is that we wish to adapt this network to the new shape, right? You don't have to retrain everything. You can keep the network fixed and refine over the latent code. So you can optimize over the latent code itself. Okay, so this is the second variant that they introduced. The third variant that they introduced would be the auto decoder. So this is already close to the auto decoder where this is basically the decoder. You are decoding this code into the SDF value and you are concatenating XYZ with the code. But you can actually condition the X on the decoder itself. The latent code would be the input. So if you do this, what it means is that you can supervise using the outputs, which is your 3D surfaces, the SDF value that you have for the ground truth. And then for every point that you condition on the decoder, you optimize over the latent code. Okay, and this itself, during inference time, what happens here is that you can actually, given a new shape, you can actually keep the parameter fixed as well. And then you just refine it over by optimizing this latent code. And that will be much more efficient to do. Okay, and that's the auto-decoder based DeepSDF. So the training would be just doing this. You basically optimize over the network parameter. So the network parameter is this. And then you also optimize over the latent code. But in this case here, you still need the ground truth. So this is the output of this is the SDF value output of the network. This is the ground truth value. Okay, and you still need this. But the advantage of doing this is that now you have a latent code to actually contrast this with this. Contrast this with this. So if you have XYZ, that you want to capture the whole shape because the whole shape is actually captured inside the network. So what it means is that you need a complete shape in order to train this well, such that the network can capture it. But if you do this version here, the auto-decoder, because it's a latent code, it's in a latent code form, right? So you are shifting the shape information into the latent code. You can actually have incomplete shape. So you can have many pieces of incomplete shapes here, right? Many pieces of incomplete shapes, up to K only. Then you have N number of samples that you will still work because you are optimizing over the latent code. Okay? You are not capturing the information inside the network weights. Okay? And there is also a regularization here. Basically, you want to minimize the variation of within the latent code itself. Okay, and this is during training time and during inference time, given a new shape. If you want to adapt the network to the new shape, you don't have to optimize over data anymore. Basically, you just optimize over the latent code. Okay, and that will be much easier to do because it's d-dimensional compared with the whole network that contains many parameters inside there. And you just need to do a refinement. Basically, this means that this can handle any form of partial observation, as I mentioned, and it can also be easily adapted to new unseen shapes. Okay, so here's some results of the DeepSDF. Basically, it can actually encode the surface very well. Okay, so this is a ground truth. It can encode the surface very well, and so in contrast to volume rendering, right? Nerf in volume rendering, there is no concept of 3D inside there. So basically, everything is rendered onto the image. That's why after you train a Nerf, right, you can also look at basically you look at the volume density. Because as I said, that the volume density, it will hit the highest value when it's on the surface, and then it will drop, right? So the thing is that you can also treat this as the level set. If you view the level set of a Nerf, after you train a Nerf, you take the volume density, and then you view the level set. You will still get the 3D reconstruction. You'll still get something like this, but it's very noisy. The reason is because they don't explicitly model the surface at all. Nothing in the Nerf formulation that I mentioned just now captures this part. Okay, so but SDF explicitly captures the surface and it trains on the surface. So that's why it's actually much better for surface representation. Okay, but there is also a problem with there's also a problem with SDF. That is, DeepSDF and all the variances requires the ground truth 3D shape for supervision. But then Nerf doesn't need this. Okay, and therefore, very recently, in the last 1 year or so, people let's marry SDF and radiance field. Okay, so basically the idea behind this is that we will, because SDF cannot do volume rendering because there's no volume density. So what happens here is that if I give you a SDF value and somehow I have a function that takes in the SDF value and convert it into volume density, then I will be able to do the volume rendering, okay, from there. And that's exactly what volume SDF does. So basically, this is the SDF function. So when you are, this x is the point on the 3D, y is on the surface. So this is the distance, minimum distance of x to the surface. When you're inside the object, it's going to be negative. When you're outside the object, it's going to give you a positive value. Okay. And what happens here is that this is SDF, and in neural volume rendering, what you are having is that you have an x value. You're going to convert it into a positive scalar value, the rate that the light is occluded at the point x. We want to have a function that takes in this and then maps out to be sigma. Okay, so if we can do this, then we successfully combine the two, and that's exactly what they done here. So they say that let's do this. Let's have a learnable function psi with two learnable parameters, beta and gamma. And psi here, so in the paper they propose, of course, there's a long proof that they show. I skip all the proof. If you are interested, you look at the paper. They show that this can be a cumulative distribution function, CDF, of the Laplacian distribution. So basically, this is the thing here. And so if you input the sine distance function here, inside this CDF of the Laplacian distribution, then you convert it into a volume density. Let's see, just intuitively see why is it true. Okay, when it's inside the object, okay, and or when any points that is far away from the object, okay, it should pick at the object. So when it's far away from the object, this distance is large, okay, because there's a minus. When it's far away from the object, this guy here is positive. Inner term here is negative. So you are looking at the left side of the axis. So when you move closer to the level set to 0, then you are actually increasing this sigma here, the volume density. So it becomes a distribution. Okay? It becomes a distribution that gradually increases. And what's interesting here is that this whole thing here is differentiable. That means that you can plug it into the network and let it learn. Okay, what is the alpha and beta here? Okay, so and when it's inside the object, because when it's inside the object, the volume density should peak because it's hidden inside the solid surface. This means that it will obstruct the particle from being transmitted at all. Okay, so that means that when it's inside the object, it's going to become even higher, the volume density. So this is the way that they propose how to convert a SDF. So basically, this is a SDF, and they convert it into a volume density here. Okay, and then basically, when you have this, you plug it into this. So X here, the sigma here. Okay, this is the transmittance. And then they derive the rendering equation in the paper. Okay, so the transmittance means that how much light it can pass through, you can be transmitted across, right? The opacity would be the complement of this, the subtraction of this with 1. Okay, and then that means that you can think of the O as the CDF and the probability density as tau. So you differentiate this, you get this, and then you put it inside this. This is the rendering equation of your neural radiance field of your nerve. Okay, but now what happens here is that, so this is the color actually. And what happens here is that this guy here, your sigma, okay, the inner terms will be replaced by psi. And then this is actually a function of your SDF. So everything becomes a function of your SDF now, and it becomes differentiable. Okay, if you look at this term here, sigma is a function of SDF and a point, and you plug it inside here, right? So now your volume density becomes a function of your SDF, and everything can be learned based on the SDF. Okay, so what it means is that you actually transform your SDF into the volume density, and it becomes, you can do volume rendering to render it back onto the image for supervision. So what it means is that you can actually learn the SDF without a need for the 3D ground truth anymore. You basically render it back. Okay, and you can see that if compared to Nerf, as I mentioned, that it's going to be very noisy because it doesn't explicitly model there's no regularization. Okay, so one regularization of that I didn't mention here, but it's well known in all the papers with SDF, is that the regularization of SDF is that the gradient of the SDF must be equal to 1. Okay, because when you move, let's say you move discretely across to the surface, it will keep on dropping by 1. Okay, so you want to make sure that the gradient of the SDF is going to be 1. And what happens here is that if you have a network that outputs the SDF, you just need, when you do backpropagation, you need to compute that gradient anyways, right? So that backpropagation, you compute the gradient of nearby points, and you just set it to 1. Okay, and therefore you can actually explicitly regularize the surface to make sure that it's smooth when it's a SDF, right? Compared with a volume density, because you don't know where the surface is. It's just the transmittance and the opacity of the scene, right? So you don't know, there's no concept of level set here. That's why in the end it becomes very noisy. But SDF, you can explicitly regularize it. That's why at the end it's going to be smooth. And in contrast, actually before this, you can also do, there are actually works like IDR, for example. What they do is that they directly render from the SDF. But because they are not accumulating the colors according to the volume density. So what they are doing here is that they render directly from the surface. Okay, that's why to apply before this paper, actually there's another paper before this called UniSurf. Okay, it actually also mentioned this. There are altogether 3 papers on this. UniSurf is another one. And but before these 3 papers, IDR, what they need is that, because they need to know where the surfaces are. So what it means is that on the 2D image, they need a mask to do the training. Okay, that's why you can see that the result of IDR is different from the others. The background are all missing. Okay, because it knows where the mask is. Okay, it knows exactly where the objects are on the pixel. And that's not so useful because you need a mask. Okay, you need to know the exact mask. So volume SDF circumvent the whole problem by saying that, oh, we just convert it into volume rendering and then we can train it the way Nerf does it. And as well as we can regularize the SDF values. Okay, any question up to this point? Okay, good. So then concurrently, there's also another paper called News. When I look at both carefully, I realized that they are actually proposing almost the same thing. Okay, so I'll tell you why. So what they say here is that it's the same thing. This is the rendering equation. So they say that the weights, this is basically a weighted sum of the color. And the weight is actually the transmittance multiplied by the volume density. This is nothing new. It's just the Nerf rendering equation. Okay. And then given the level set of S here, so they say that there are two requirements on this weight here. Inside this news, they claim that there must be two conditions. These two conditions must be satisfied in order for this thing to hold, or in order for the SDF to be put inside this volume rendering equation. First, it must be unbiased. That means that because you are looking at the weights here, unbiased means that when the weight peaks, so let's say you have certain distribution of the weight. When the weight peaks, that must correspond to your sign distance value. Okay, that means that this T star here, which corresponds to your sign distance value of 0, okay, on the surface, that is where the weight must peak. Okay, and the second thing is that it must be occlusion aware. That means that if you have two depths, T0 and T1, and T0, T1, where T1 is further away from T0, if the SDF value are the same, okay, then the weights of T0 must be greater than T1, because you will pass by T0 first. And if what this means is that you have T here, T0 is here, T1 is here. And what this means is that you have two surface, you have two objects here. So if you pass by this, you have a ray passing by this, then the weights here better be higher than the other one. Okay, the reason is because it's already occluded by the first object. Okay, the first value here. Right? So there's no point of accumulating so much of this, the whatever that is behind the first object. So these two conditions must be satisfied. And basically, in the paper, they say that if you choose the conversion value, so F here now is the SDF, X goes into F and outputs the SDF value. Okay, and then let's say I call the psi function as a transfer function that transform the SDF value into the volume density. Okay, basically T is also a function of sigma. Okay, so width becomes a function of sigma as well as a function of the sign distance value. So they say that, they claim that if you choose the weight to be very similar, that means that this distribution of sigma here, okay, to be very similar to what Nerf is doing. Okay, then with respect to the depth values, okay, then you have an offset between the surface. So this is T star is where it corresponds to the surface. That's the level set. So they say that if this is the same as Nerf, then basically there's an offset between where the weight peaks and the level set. And this is not correct. Because what it means is that your radiance field, the accumulation of your color, and it doesn't correspond to that surface. By right, the color that you are looking at should be from the surface. So if you choose it to be the weights to be this unimodal distribution, for example, a logistic density distribution, then that is basically the offset between the weight. It doesn't peak at the surface. So that means that the color that you render back is actually offsetted from the surface. Okay, the volume rendering. And what they do is that they propose this. They propose that instead of using this sigma here, they propose rho. And rho should be computed from this function. Okay. But what I observed when I was looking at this carefully, so basically they say that if you replace this rho here, the sigma with rho here, then instead of having this green curve here as the weight where there's an offset, now the peak of the weight corresponds to the surface. But what happens here is that your sigma will no longer be unimodal like this, the logistic function. it becomes an S-shaped curve here. Okay. So in this paper, they claim to be this. Then when I look at this curve, isn't the same as this curve here? It's the same thing. Volume SDF already tells you that there's no need to choose this. You directly choose this. And the Laplacian, which is exactly the same as what they have chosen here. Right? So now everything coincides. So condition 1 is satisfied in the paper. This means that the weight must peak at the surface. Condition 1 is satisfied if you choose this. And there's also a long proof in the paper, but I will not show the proof. I will just show the illustration, an example here. So what happens here is that if you choose rho to be this here, then if you have two surfaces and a 1D dimension of that, suppose that T0 is here and T1 is here. So T0 is here and T1 is here. Okay. When you are looking at this ray, you hit this one first. So that means that, and if you imagine that this object is not there, you hit the other surface. So both this SDF value and this SDF value would be the same. They will be equal to each other, which means that I'm actually looking at this condition here, okay, where this is satisfied and this is also satisfied. And then what happens here is that if you use rho and compute the weight here, you will get this weight where both weights are actually more than 0. Actually, it's more than 0 everywhere. Okay, so this condition is satisfied. And because you are looking from here to here in this direction here, so the weights, don't forget that the weights is actually the cumulative weights of the color. So the first surface should contribute most to the rendered color because the other one is occluded already, right? So the weights of T0 must be more than T1. Okay, and they show that this is true. Actually, they prove it in the paper. Okay, but here is just one case, one illustration, and therefore the last condition here is also true. Okay, therefore the second condition is satisfied here. Okay, let me quickly go through the remaining parts. Okay, so this is how they marry SDF and volume rendering together. And but there is still one disadvantage of Nerf. That is, it requires known camera poses. Okay, so in BAF, what they do here is that they assume imperfect camera poses, and then they do bundle adjustment together with the with Nerf. Okay, but actually BAF still requires some initialization. It cannot be totally random, the poses. So basically, if you look at 2D image alignment, you can have two views, okay, I2 and I1. You can have a warping function that takes a pose of the image and any point on the image. Okay, you can warp this. What this means is that you are warping one patch here into the other patch, the other view, I2, and then you basically minimize this error. This is the photo consistency error between the two views. Okay, and this can be iteratively solved because you are trying to optimize for the pose. Okay, if you know the pose, you can actually do this warping, and by just minimizing the photo consistency. So if you do a Gauss-Newton, then A here would be simply J transpose J. By now, all of you should know this already. Okay, this is what we learned during bundle adjustment. Okay, and then delta P will update this, and the Jacobian here is the warping function. So this can be obtained numerically. That means that you set a point and then you take a delta and put it into the function. You subtract the 2 and divide it by the delta. Okay, that will be the Jacobian. Okay, and then, so if now this is that you have two images, you optimize for the photo consistency. Okay, but now let's replace one image with a neural network. That means that you are going to render that image using a neural network. Okay, so what happens is that one of the image becomes a neural network. You can do it for the other image as well, right? So you can consider both of the images as well. Okay, and now one of the image becomes a neural network. That means that you render it onto the other view and you take the subtraction of this. So you can also optimize over that neural network, okay, and minimize the photo consistency over the pose. So if you consider two images on both sides, this is what you can do. Basically, with summation 1 equals to n equals to 2. Okay, and now the Jacobian, if you take the partial differentiation and update it this way, the Jacobian now here is no longer obtained numerically. This is simply your backpropagation. Okay, it becomes, because this is a network, so you can do a backpropagation, compute the Jacobian and update it. Okay, and what's interesting here is that this is just you are replacing it with a general network. But if you replace it with Nerf, so you render this image using Nerf, okay, from one view to another view. Okay, this is what you render. Basically, if you have multiple views, you can take any view and render it across all the other views, okay, and optimize over the poses. So now this thing here is going to become a function of the network parameters, which is what you are going to learn using Nerf, as well as the camera poses. So the camera poses can be computed. It can be used to compute any pixel and the depth. Okay, when you know the pixel and the depth, meaning that you know the 3D point, you can render it back. What this simply means is that you have Nerf, right? What you are doing is that you need to know the direction. You need to know this point, X. So this D and X is actually dependent on the camera pose, right? So now you can actually express this X as a function of P. And if you don't know that, right, you can optimize it together inside there. So basically you need the correct P in order to know this X. And you also need to know the pose of this in order to render it back here, right? So that's what this warping function is all about. Because you can consider this integration. This integration becomes a summation, as what we have seen earlier, right? You can consider this as G, as a function G. Basically, your network outputs C and sigma, which is 4-dimensional. You have n of this, and then it's going to map into RGB value. It's going to map into this RGB value onto your image. So you can actually put it inside here, and then do the Jacobian, compute the Jacobian. You'll be able to and basically you are able to optimize this then, right? So it will be you are optimizing over your Nerf as well as the camera poses of all the multiple views. So this allows bundle adjustment to be incorporated into Nerf. Okay, so instead of minimizing the reprojection error, you are minimizing the photo consistency, the rendered image and the source image from that view. Okay, and you can do this over multiple views. But there is one problem with this, because in order for Nerf to be with high fidelity, you need to do the frequency encoding. But what happens here is that if you do a partial differentiation, you compute the Jacobian over the frequency encoding here, okay, then what happens here is that you can see that the Jacobian is affected by the order of your Fourier basis. So that means that the very high frequency part of your Fourier frequency will dominate the Jacobian. And if it dominates the Jacobian, basically this is what you are trying to do, right? I plus 1 and I plus delta P. So the Jacobian will be used to compute this, right? Delta P would be equals to J transpose J inverse multiplied by J transpose the error, right? So if your high frequency component is there, That means that this guy here is going to be dominated by the high frequency components of your, and it's always there because you encode it this way, right? So the initial training would not be good because it's all taken over by there's no chance of minimizing the low frequency part. And therefore, they weigh this frequency, they propose this to weigh the frequency. Okay, so it's a 0 to L controllable parameter where they use this to control during the initial phase of the training, they weigh it down. So that means that all the higher frequency components are not there initially. They only use the low frequency to control it, to train the network. And then thereafter, they gradually increase, they add it back, the higher frequency. Okay, because at the end, it's going to be already well trained. And then you add back the higher frequency. So it wouldn't affect the training so much. Okay, and that's BAF. But BAF also has a disadvantage that it's not generalizable because it's still taking in this. Okay, the encoding is still taking in X, the 3D point and the direction. So in our work, we actually use IBRNet to substitute this. Okay, we combine the two together and they are updating the absolute poses. So all the P here are absolute with respect to a global frame. That's why they still need to have substantially good initialization in order for it to work. But what we did is that we are inspired by the global structure for motion. I have actually talked about this in the bundle adjustment lecture. So we instead update the relative pose. So relative poses is easier to, it's also bounded. Okay? And the network can actually learn this better. So that frees us from the good initialization. And we show in the paper that we don't need any initialization at all. Just some random initialization and it still works. Okay, and this is BAF, this is the result. So you can optimize and then the camera poses optimize and it will work. All right, so the last part that I want to talk about, I might go over time a little bit, but let me finish this. The last part that I want to talk about is dynamic scene, okay, specifically for human. Okay, so because this is interesting, because if I can model the human and I can manipulate the human, okay, I would have a digital avatar. So if I take a scan of you using this and then I build a digital model, Nerf digital model or SDF digital model of you, then basically, and if I can control this, become animatable, then I can actually make a metaverse out of this. I can put you into the metaverse and control how you look like inside the metaverse. Okay, so but the problem here is that how do we, because it's dynamic, the human, for example, this guy is dancing. So and this point on the hand here, because you know that in Nerf, you need a static scene and known poses of the camera, because you need to do this. Every point you need to know where it renders back, right? But then if this point moves in the 3D scene, how do you know that this point is the correct point correspondence? Okay, at time t equals to 1, it's here. Time t equals to 2, it might be here. Despite that the camera stays fixed. Okay, how do you actually model this, the correspondence? So the way to overcome this is to construct what we call the canonical space. Okay, you have an observation space, which can be any pose, but the canonical pose would be, the canonical space would be a T pose. Okay, it will be a T pose. So what you want is that given a ray at any point on the observation space, you want to map it into the canonical space. And then what you want to learn is that in the canonical space, you want to learn all the features that corresponds to that canonical space and map it back onto the image, okay, as a radiance field. So This means that you are actually storing all the features on the canonical space, the corresponding features on the canonical space. And once you are given observation space, you know that this point here corresponds to this point here, for example. Then you want to retrieve that feature from the canonical space and use Nerf to map it back to retrieve the color and radiance field and the volume density, and that color and volume density of this point in the canonical space will correspond to the observation space, and then you place it back into the corresponding observation space. Okay, so this is how they do it. But the question is that how do you know that this point corresponds to this point, for example, from the observation space to the canonical space? And that can be done using what we call the linear blend skinning. Okay, so suppose that I want to map canonical to observation space. This is a point on the canonical space. Okay, this point here, which I have a canonical space, and I want to map it into observation space. So it will be a linear combination. This would be basically the transformation that and I want to know there will be a linear blending weights. Okay, the blending weights that I need to learn. And this blending weights is actually a function of V itself. Okay, and then if I want to do the opposite, I simply take this whole part here and invert it. Okay, and then I'll get it from the observation space back to the canonical space. I think there is a typo error here. This should be the yeah, it's the, because this is the opposite. Okay, and the x prime should be here. Okay, so you can take this, and then what they do here is that what they propose here is that they propose to design a network, okay, such that it outputs the blending weight over here. And this outputs of the, because G here is nothing but just the bone transformation between the joints. Okay, and it stays fixed. You can actually use SMPL. There's a model called SMPL, simple model, and to estimate all these parameters over here, given any image or a bunch of multi-view images. You use this to, but SMPL has the problem of it's actually it's actually a model of the human with minimal clothing. Okay, but if you want to model the human, you also want to model the clothings as well. But the clothings are deviation from the minimal clothing human model. This is where what we want to learn here would help to encode the deviation from the SMPL model. So you can see that that's why there's a delta W here. Okay, this is the human model that we can, the SMPL model weights that we can compute directly from the image. And then we want the network to actually predict the deviation away from the SMPL model to give us the final weights over here. So this would allow us to compute the mapping from the observation space to the canonical space. And then the next part here is that we need to learn this part here. So once we know the canonical space, we need to learn how to map every one of this into the color and volume density. And basically that's just the Nerf equation over here. Okay, and here, this part here would also be, we also have another part over here where it helps us to invert it actually learns from the canonical space back, weights here back into the observation space. Okay, so that means that this weight here is actually doing the inverse. It's actually this W0 here, and compared to W over here, which is this part here. Okay, so you can see that if W canonical takes in the transformation of X, transform into from the observation space, if we can transform it into the canonical space, then we put it into this weight here. Basically, the outputs of these two, the output of these two blending weights should be the same thing, okay, because we are inverting it, okay, and therefore, this can act as a regularization to our network here, okay. But there is a problem with this. If you do this, there's a problem with this. That is, it's not generalizable, okay, because once you train it, basically, you have a network that outputs one canonical space. And that canonical space is stuck with the identity of this person. So you cannot generalize into another identity. But this is animatable. What I meant by animatable is that, because if you change the observation space, if you, let's say I animate this host, okay, I give it a different X over here. And I say that there is, I want a different view over here, is able to pick it up from the canonical space and map it into this X that I desire. Okay, so that means that this whole thing, I can actually control the rendering, okay, into a different human pose. And you can see that from here in the novel view, and you can do novel view synthesis. And it can also do a novel pose. That means that you can control the pose and you will render back to a new pose over here, which is pretty much like the round trip over here. But again, these things are also actively researched now. Okay, so it's still not fully solved. You can still see that the quality of the rendering is not perfect yet. Okay, so is still actively being solved here. Okay, and there's two limitations to this. The first limitation is that it requires pose optimization. Okay, that means that if you want to render it to a new pose, okay, you need to optimize over the latent code over the new pose. So S here is actually the new pose. It's computed from SMPL. I'm leaving out quite a lot of details in the slide, but this is actually from the SMPL new pose. So you can input this new pose, and then you optimize over the latent code, the new latent code. And then you can actually use this refinement of the new latent code to infer the person in a new pose over here. Okay, but it's not it requires proposed generalization, and it cannot generalize to new identity. So it's not generalizable per se. Okay, and the first problem here for pose optimization, we can have a solution here. That means that because the blend weights here is dependent on the observation space, which means that it takes in X as your input over here, okay, in order to give the X prime over here. That's why it cannot be generalizable to different poses. Okay, it's actually pose. What you can do is that you can actually make the blend weights over here pose independent of the canonical space instead of the observation space. That means that instead of this W here to be a function of X in the observation space, you make it a function of X prime instead in the canonical space. So now it becomes independent of the input pose. Okay, and therefore it will be able to generalize it. But what happens here is that actually this is a more correct version. If you do this, what happens here is that it involves some form of root finding here. Okay, because now you realize that the weights over here, you are using these weights here, while you are using this weight here, to find X star or X prime over here. Okay, but then you realize that the weight now is a function of your output. Okay, so what it means is that you need to solve for the root of this equation. Okay, because now your X prime here, it becomes a function of, so you see that X star is here. Okay, that's your final canonical space pose. but W here is a function of X star, which is actually your output. Okay, so in the end, what you need to do is that you need to solve for the roots of this equation over here. It cannot be solved in closed form now. So the way that we solve for the root would be to use you can either use the Newton-Raphson method, or you use a quasi-Newton method as proposed in the paper. So this will involve some root solving of the, basically this is W, which is a function of, which is actually your network here. Okay, so what you want to solve is that you want to solve for this X here, and that X should be the same as this output X prime over here. Okay, and you will involve a lot of iterations over here. Then you can also do multi-correspondences. That means that this will become you initialize with a vector over here of all the X. That means that you can solve for multiple of these X, multiple points at the same time. But it will all be inside this Newton-Raphson or quasi-Newton methods. Okay, and this is Nerf. So in the end, what they do here is that once you have this, now the blending weights is independent of the post. That your input here is independent of the post, and therefore you can make it generalizable because now you decouple this input from the canonical space here, right? So whatever input that you give, you just need to solve for the root, and you will give you the X star over here, and you can retrieve that point, okay, directly from here. And once you retrieve, this is where it stores all the features F. So once you retrieve the feature, you can actually output it on X prime, which is actually at this point over here. Okay, therefore you will be able to infer the output SDF over here. And by the way, SNRF is only meant for SDF. When they designed this, they designed it using SDF. So there's no normal view synthesis over here. Okay, but what happens here is that you can now control the pose of the human. Okay, by inputting a different pose parameter, you can actually infer the final output over here, the surface output over here, using a different pose. Okay, and here's how you compute the. It's fairly computationally expensive here, because what you do here is that when you do the loss function, you partially differentiate with respect to the two parameters. One is the one that you learned the features, okay, to infer the occupancy, which is sigma f. The other one is the weight parameter over here. So when you infer the weight parameter over here, you need to partially differentiate delta x star with delta sigma w. But this guy over here requires you to solve this root finding equation, because you need to solve for x star, where this x star here is actually the input of your deep network. Okay, and there is no closed form equation here because this is a deep network, right? Because what you are doing here is that you are actually taking the output as input to this network, and then that will output the weight for you to compute x star or x prime written here, right? So basically there's no closed form here, and it becomes this equation over here. So every time you do the back propagation, you need to compute this partial differentiation, and that will involve you in solving the this root finding equation. And what happens here is that you can actually evaluate this, and you will require to do something called the implicit differentiation, okay? Because this is an implicit function over here. So you need to do an implicit differentiation, and then the operating point, in order to find this, you need to find x star, the operating point to compute this Jacobian over here. You need to do a root finding in order to find the operating point before you can do the backpropagation and update it. Okay, but this is a more correct method. This is a more correct method because the reason is because of this equation over here. Okay, because this equation over here, right, you can see that you shouldn't actually invert the whole thing. you shouldn't actually invert the whole thing. But if you bring this towards this side without inverting it, you can see the X actually appears on both sides. Okay, and you need to actually solve for the X in order to get the correct bending weight. This means that in order to get X, so without inverting this, you bring this whole thing here. In order to get X, you need to know X in order to solve it from here. Okay, so this means that it's actually, there's no closed form equation. And by doing this, right, it's actually a very big approximation. You are simply just assuming that this whole thing can be inverted, and then you are replacing this weight over here as a parameter of X prime, which is what is done here, right? So this is not correct, or mathematically this is not so correct in terms of the linear bending weight. So this is actually a more correct way, the Nerf, but it's actually extremely slow. Okay, because it requires the root finding, but the result is actually better. And you can actually do it for extreme poses. You input an extreme pose and you will output the correct pose over here. The second part, the second limitation is that it cannot generalize the new identity. The reason is because, as I mentioned, that it actually relies on the T-pose. Okay, so what you are learning is that you are learning a T-pose and that stores all the features on the T-pose. And this is not generalizable. So instead of using the T-pose, let's relax it to no T-pose at all. Okay, but then the problem of doing this is that now you have to find all the correspondences. Okay, this can be done if you have multi-view, multi-time step. This can be still done because using a multi-view, you can output the SMPL model here. So every multi-view that you have over different time, although the person is moving, you can output for every single time step, you can output the human SMPL model, and you know the indices. You know which vertex corresponds to which other vertex in the different time step. So you can have a rough idea of where this is going to be. Okay, and then what happens here is that now you can do away with the T-pose. You can link this up and directly pick out the features from the image itself instead of storing it using a T-pose. Okay, you can directly pick up these features. And now in this neural human performance, which was published in NeRF last year, I think, or the year before, I can't remember. Right, so there are two steps to it because it's multi-view, multi-time step. So you need to fuse these features together over multi-view and multi-time step. So what they do is that they introduce two transformers. One is the temporal transformer, and the other one is the multi-view transformer. So temporal transformer is that this point that's seen over multiple views, over different time steps. I want to fuse all these points together in a temporal transformer. So basically, this is just introducing a transformer where you can finally fuse all the multi-time steps features correspondence into the output features over here. Okay, so basically you're fusing it over multiple times, and it's the standard transformer that we have. So once you have this feature over here, the next thing is that we can actually put these features into multi-view. Because you have multiple views, you also want to fuse the multiple views features together. Okay, that will be another transformer. Okay, so they just input the this is the output from the temporal transformer. Okay, they just put this, and then you have multiple camera views. So these are from each reprojected pixel onto each image. You pick up the feature over here, and then you fuse it inside here. Basically, you are doing a cross attention over the temporal features as well as the multi-view features over here. Okay, then finally you get a final view-wise features over here, Z, and then you learn the MLP from this final feature to output the volume density and the color. Okay, so as a result, this is probably one of the best results now. Okay, and Yeah, I think that this is kind of interesting, but they still require multi-views. Okay, that means that a lot of views, and in order to produce the good quality result over here. Okay, any question to this point? If not, then I guess this is the last thing that I want to talk about for the entire course. So today we look at the neural radiance field, volume rendering, and I talk about the issues of neural radiance field, which is the generalizability, the efficiency, and I talk about some methods to mitigate this. Then I also talk about the sign distance field, okay, and compare the two. Then finally, we look at how to marry the two together such that you can do a self-supervision, which is volume rendering, but yet maintaining the surface accuracy using sign distance field. Then finally, I talk about how to use Nerf and SDF to do animatable and generalizable dynamic humans. Okay, so with this, I conclude the whole semester, and thank you.